3, boom. Hello and welcome back to Calculus 2. Today's lecture 6.3, disk and washer method. The textbook calls it volume by slicing because the idea is to take the object and slice it perpendicular to the axis of rotation. Now, what does that mean? Well, if I have some kind of a cylinder, that cylinder is going to have an axis of rotation, and hopefully you can see that if I draw a constant line above x-axis and I rotate that line around x-axis, it will create a third-dimensional object called cylinder. It's a pipe. Now, we can find volumes of such objects just using a certain formula, which I will explain. But before we actually get to compute anything, it's very important to understand how these objects actually work. So I'm just going to ask a few questions. So let's say I have a y-axis and I have a line like this. What would this create? It will not create a cone, but it will be very close.
Oh, sorry, that was
it rotates on the y. It rotates on the y-axis. Don't worry about you in the third row. You're not here. Park, put it up, man. Put it up, high up. There you go. Yeah, coffee cup. Do you see that as you rotate this, you get, right? You get a coffee cup. That's okay because it's going to stay warmer longer. If you get the skinny, tall cup, it cools faster. If you get the fat, wide cup, it cools much slower because the shape is closer to the sphere. Sphere has the slowest diffusion of heat. So when you're picking your cups, pick them for the occasion, right? If you want the coffee to stay as, right? So we have a coffee cup over here. We have a pipe over here. Let's see if I can draw this. What's that? Baseball bat, exactly. So that was on x-axis, right? Light bulb. There we go. Let's start right away with crashes. The stream is barely working, and now this thing is going to start crashing. It's going to be awesome. So hopefully, right, you see how this thing works. The question is now, how do we utilize integrals to find volume of such things? The most important part to understand here is that you have circle. Every time you cut these shapes perpendicular to the axis of rotation, the intersection will be a circle. So the baseball bat you will cut this way and you will get circle. The coffee cup you will cut again and you will get the circle. So every time you cut an object, you will get a circle. We know that the volume is area of the base times the height. Now, anytime we cut the object perpendicular to the axis of rotation, you get circle. which means that the area of the base is given by a circle. Well, we know what the area of a circle is. And then you need to multiply by the height of the object. So let's dissect the, let's say, coffee cup, right? I'm going to take the coffee cup and put it sideways, like this, and think about this object for a sec. If I place the object on x-axis, cutting it, right, will give me the intersection, and I'm cutting there a very thin disk, right? So this is a disk over here that I'm cutting out. That disk clearly has a circle as its base, and the height of that disk is delta x, right? The height, which means it's the width, because we put it sideways, but if you stand up the cup, the delta x would be the height. So if you're thinking about this a little bit, right, you would say pi r squared dx. Well, maybe I should put delta x, right? But then you realize that your r is changing as the function is changing. For it is this r, which is the function that governs what kind of object you get with the rotation. Is it a cup or a baseball bat or a light bulb, or what is it, right? So it should just make sense that the volume is integral pi f squared dx. It should just make sense that that's the formula. Let's see if we have to restart every 15 seconds. So volume is integral a to b, again, which are your a to b limits of the object. And then you have pi f squared dx. Dimensionally, it makes, yes?
So the f of x, that's the radius?
Yes. So now, if you look at this, you have volume, and the volume is 3D. Do you have 3D on the other side, on the right side? The answer is yes, because you have function, which is y. That's a dimension, but then it's squared. And then you have times dx. So you do have 3 dimensions. There's 2 d's here and 1 d there, altogether 3D. So the formula makes sense dimension-wise. And you have the function f squared, right, which governs what type of object you have. So now when you go back to whatever shape you want, as long as you know what is the shape that creates that object, what is the function that traces this line, you are able to rotate that, and that is the f that you would feed into the formula to compute the volume. I can stand this up and just have integral c to d pi f of y dy if I want f squared y dy if I want to have dy, which would be better for our cup. So now I get to write the formulas for disk method. Volume is equal to pi integral a to b f of x squared dx, or pi c to d f squared of y dy. First exercise for you guys, find the volume of the cone generated by y equals 2x around x-axis on 0 to 3. This is the cheapest question that you can get in Calculus 2. So, there you go. We are starting Calc 2 with the cheapest possible question you can get. So find the volume of the cone generated by y equals 2x. You revolve around x-axis and 0 to 3. Draw the segment, draw the rotation, draw the shape, right? Draw the entire cone. You get the fun stuff. All right. So let's take a look at the problem together. The first part is me drawing the 2x, and then it's going to go this way, and we're going to have this really interesting looking cone, right? It's really squished. And if you play Mortal Kombat, you know this is Raiden's head, but different. So we are from 0 to 3. That's what we have. The volume is 0 to 3. Function, oh, I forgot pi. Don't forget pi. function squared dx. So I have 4x squared. So pi integral 4x squared dx 0 to 3, which will be pi 4/3 x cubed 0 to 3. And that's going to be 936 pi. Is it 36 pi? Now, if I gave units inches, it would be inches cubed, right? Because you have to use the same units later that you convert that. What is this needed for? Well, you have reservoir tanks, right, for airplanes, cars, and things. They might be this shape, whole bunch of other stuff. So you need to be able to use correct units. If the units are present, the answer will be 1 point will be allocated to correct units for each answer if the units are present in a problem. So this is basically what it is. Now let's see one more example. So rotate y equals 2x on y-axis. Again, 0 to 3. Now these are x values. Observe that I am using the same function, the same x domain, but now I'm rotating on y instead of x. If I'm rotating on y, what integral do I have to use? Other one. Yes, the other one. dy, okay, fine. All right, use the other one. You get to draw again. Are you expecting the same answer? No. Good. As soon as you draw the picture, you will see that it's much different. Yes. It helps greatly, but I don't know. Mm-hmm.
So we're making a cone around the y-axis now, and we're using x values to, take our segment from that cone. X is just a line in that dimension. Now, if you're cutting it like this, this is our graph,
Mm-hmm.
and this is what it looks like. Is that like half of a coffee cup? Or no, sorry, it's the whole thing.
Mm-hmm.
Just half a cone. Curious to know what that looks like.
Well, it's going to be a cone. It's going to be a cone like this. Yeah.
Or half a cone.
Cool. You can't get halves with rotation. Rotation always gives you the rounded object.
Yes, but the x value is from 0 to 3.
Oh, that just tells you that you'll have to convert that because it's useless. It's a dy integral.
Yeah.
Well, it's not useless. You have to, yeah, useful, exactly. Uh-huh. All right, so let's take a look at how this looks like. So again, I'll have the 2x, and then when we rotate on y-axis, it will come out on the other side, and the cone will now look like this. Now remember that this portion here is 3. If this portion here is 3, how much is the top of the cone? 6. Your limits of integration are 0 to 6 because your dy integral is y1 to y2. So you don't get to use your x values. Be very careful about those things. Remember what I said on the first day last week. I said x, 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 right? X, 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 y, 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 y. So I gave you the function y in terms of x. I gave you the domain in terms of x. And then I asked for dy integral. This means that you have to immediately switch everything to y. Your function becomes x equals 1/2 y because you need f of y. And your interval becomes 0 to 6 because you need y limits. So your volume is pi integral 0 to 6, 1/2 y, everything squared, dy. What happened? So do we all see dy over here? dy immediately tells us that the limits must be y and your function has to be in terms of y. Bueno? How you say good? It's not bueno. Dobro, dobro. All right, so we integrate now and we're done. So this is going to be pi integral of 1/4 y squared dy, 0 to 6, pi 1/12 y cubed from 0 to 6. One of the 6's will cancel with pi. Another 6 will cancel 2, so 18. 18 pi? Yeah. It's obvious. So we have 18 pi. Please observe that these two problems had the same function, the same domain. It was a different rotation. They have different answers because they created different shapes. If you look at this shape, it's what we would call a normal cone, right? Normal cone. Yes, it's inverted, tough luck, right? And then when you look at this one is really wide. And it's kind of, right, if you put it up, right side up, it will be not as tall. Great.
How do you end up with different answers with the same shape?
It's not the same shape. Look at the shape here.
Well, yeah, I know.
Look at the shape here.
Graph where we're taking the same cone.
It's not the same cone. This is where the cone is, right? It's really fat on the bottom, very short.
Because you're wrapping, it's a different, okay.
Same function wrapped around the different axes. Now, I can get them to be the same if the function was y equal to x, and then rotation on x or y-axis, it wouldn't matter, right? Because y equal x has 0 to 3. This way, 0 to 3. That way, no matter which one you rotate on, it would always be the same cone. But because it was 2x, right, they're different. let's pick up an exercise in textbook. So now this computer keeps signing out. Perfect, that's not what I wanted. Problem number 19 in a textbook. I know how much you love these types of functions, so here we go. Y equals e to the negative x. Y equals 0. X equals 0. X equals ln 4. Rotation is on x-axis.
I'm used to that. Yeah, he's always used to it. Yeah, you get the whole fucking day with me. What did he have? Yeah, you figured it out. Guess what? My
Yeah, I just don't need to do it. No, it's not funny now. I don't know. No, you do well. Think about it. Yeah.
That's smart anyway.
The trick is to study all the time, small increments, and I like it, so I will take all the fine parts get over with rather than, try 15 times.
I would rather have like because I don't like having things talk to each other.
No, you take one time at a time. You finish one time and then
Yeah, but like, but
no, I thought you were supposed to take all three, like the physics, then down the book.
yeah.
No, I always said 30 minutes. But like take probably you do number one here, then you do number one here, and then now you have a one that way. Technically, then since you have only one time frame, you're getting triple. Maybe write 2 pencils. Write 2 pencils. Is there an exercise
Yeah.
Yeah.
All right, let's take a look at this problem together. It's tons of fun, right? Draw some pretty pictures, put some integrals down, and call it a night, right? So we have an exponential decay function. So that looks like this. Goes through 1. And then you have your ln4 somewhere. We don't care where it is. Just ln4 is a number. So now, what do you have? You have this region completely sectioned off. We are rotating on x-axis. So we are immediately, this means dx, right? So now, when you look at this, you have everything you need to find the volume. Your limits are, oh, forget the pi. Pi, limits are 0 to ln4. Those are numbers, right? ln4 is a number. So your a and b are 0 and ln4. Your function is e to the negative x, that gets squared, dx. Exponents multiply. So we have pi integral 0 to ln4 of e to the negative 2x dx. As I integrate this, eventually, when you integrate 5 million of these, you will know that the integral is e to the negative 2x over negative 2 from 0 to ln4. We have a negative pi over 2. And we have now to plug in ln4. When I plug in ln4, I will get e to the negative 2 ln4 minus e to the 0. Negative pi over 2. Now, this is a negative 2. It will go as the exponent of 4, and it will make it into 1 over 16. So this is e to the ln 1 over 16. because negative 2 as the exponent is technically squaring in the denominator. Everything minus 1. Ln and e cancel, so this becomes negative pi over 2, and then you have 1 over 16 minus 1. That's going to be negative 15 over 16. So negative and negative die, so this is 15 pi over 32. I hope. Bueno? Good enough, right? Move on. Yes.
Piece of information that said y equals 0. How's that relevant to this problem?
Y equals 0 is your limit here. Y equals 0 is x location, right? Y. Oh, sorry. Y equals 0 is the x-axis, and okay, guys. So x equals 0 is the lower limit. Y equals 0 is the bottom of this. Is the bottom of the shape. It's bound from below. The next example actually is answering your question, because now we are going to rotate two functions. If you look carefully here, isn't this just like the area above the curve, and we rotate that? Can I have two functions intersect anywhere? We can rotate that, right? And if we rotate that, we are going to have a hole in the object. So when you rotate a line, you are not getting a hollow object. When you rotate a line, you get a solid chunk, all right? It's full of material inside. But we know that this is hollow to store stuff in there. So there is going to be a thickness to this plastic. So you're going to have one line, let's say at x equals to 5, and another line at x equals to 6, right? And then you rotate those two, and you rotate those two around. The material is between 5 and 6, and everything between 5 and a 0 is nothing there, right? So now what I'm going to do is I'm going to create a hollow object. I can do it technically with anything, but let's just do the simplest possible example first. So say I rotate two lines like this around x-axis. If I rotate two lines around x-axis, you are going to have, let's say these are 5 and 6 lines, and let's rotate them from 0 to 3, whatever. We are going to create a cylinder-looking object, but it will be hollow inside. So what do I get? I get something that looks like this. When you look from the end, the top, right? Looks like that. There's a hole. It's a pipe. Pipe. What is the volume for this? Guys, remember how you took the regular area between the curve and you created area between two curves by subtracting integrals? It's a difference between the two. So it's going to be f squared minus g squared. All right? So volume now is f squared minus g squared dx. Cool? Of course, cool. It's Calc2. Come on. So what do I get? I get pi 0 to 3. 6 is further away from axis of rotation. So further away minus closer by dx. Pi, that's 36 minus 24 is 11. 11x 30, so 33 pi. What happened? Oh, one like this? Yes.
You find the thickness of the thing from the
Right.
So you have an inner radius and an outer radius.
Very good. And that's exactly what's happening here. We have the inner radius up to here and the outer radius up to here. So now this is called the washer method. And the formulas are, volume is pi integral a to b f squared minus g squared dx, or c to d f squared of y minus g squared of y dy. So one or the other. Fill in the blanks. So washer method. Why is it called washer method? If you take and cut the hollow object, you get washers, right? You know what a washer is. It's a little... yeah, it keeps disappearing because it can't sink to the cloud, which is the reason why the whole thing crashes and so on. Well, it has issues of sinking with the cloud. There's no little green thingy over here. Then whenever it doesn't sink to the cloud, it erases it. It's not important. And that's that. Well, you want to go?
No.
Huh?
We didn't even get the show back. Oh, that's nice.
There's always Wednesday. So do as many of these as you can, and I'll see you on Wednesday.
Wait, Lou, are you coming tomorrow?
Yeah, I'll be doing this whole tomorrow.